Okay. All right. So let's see. Last time we finished with right this discussion of the Poisson kernel, and we were talking about Boozerman function also, which is a function of three variables, right? So yeah, let me just clarify this proof that so we saw if I take 2 points x, y and a boundary point xi, then the Boozerman function is equal to the limit for any geodesic ray gamma with endpoint xi of distance x gamma t minus distance y gamma t. This limit exists and is independent of the choice of ray gamma that we saw by asymptotic convergence of geodesics, exponential convergence of asymptotic geodesics. And this limit also is equal to the more general limit as z tends to xi in the cone topology of distance xz minus distance yz. So let me just quickly give you a brief sketch of the proof of that. Where did this go? Okay, one second. Oh, where did the last page go? Just, got a bit messed up. No, not this. Oh, the order of the pages is messed up. One second, sorry. Here. Fine. All right. Okay. So let's just prove this. So we have xy in x and xi in boundary x. And we're looking at the limit as z tends to xi of, so here's y, here is x, distance xz minus distance yz. So what I can do is, if I fix a t large, okay, then I can take a point, say zt here, along the geodesic from y to z, and I look at the geodesic ray from y to xi. So zt will converge to the point yt at distance t along the geodesic from y to xi, right? Yes. This is by definition of the cone topology. Okay. Now what am I looking at? I'm looking at distance xz minus distance yz. Okay. Now I want to compare this with distance xzt minus distance yzt. So if I subtract distance xzt minus distance yzt from this, then I'll get a minus here and I'll get a plus here, right? So if I look at distance xz minus distance yz, this whole thing minus distance xzt minus distance yzt, right? Then I'll get cancellations. What will remain is this distance minus these two distances. So that's xz minus zzt minus ztx, right? Okay. So that's the defect in the triangle inequality in this triangle. Okay, so but if I look at this picture, then I can say that because the distance xy is fixed and the distance xzt and yzt is large for t large, right? For t large, that implies that the angle at zt, the comparison angle at zt between x and y. Okay, let me write it as a comparison angle. So this angle at zt between x, y, this is small, right? Is that clear? Yes, is this okay? Yes? Yes, are you there? Hello? Yes, can you hear me?
Yes, sir, it's clear.
Is this clear? You just take a comparison triangle, right, for these 3 points. Then this distance is t, this distance is t plus big O of 1, because this side is fixed, this side is big O of 1. And so you use the hyperbolic law of cosine, this angle theta will be small. It will be of order e to the minus t, right? Is that clear?
Yes.
Okay. This is big O of e to the minus t. Okay. But then what can I say? I know that the comparison angle, if I look at this angle, then the angle at zt between zx plus the angle zt between xy, this is greater than or equal to the Alexandrov angles, right? So the angle at zt between zx plus the Alexandrov angle at zt between xy, and this Alexandrov angle is equal to pi, right? So that implies that the angle at zt between zx, the comparison angle, this is greater than or equal to pi minus big O of e to the minus t, right? Yes? Okay. Yes, can you hear me? Hello?
Yes, sir.
It's fine? Yeah. So if this angle is close to pi, right? If this angle is close to pi, then what do I get? I get that I'll have almost equality in the triangle inequality, right? Yes.
Yes.
If this side is A and this is, or if well, this side is C and this side is A and B, right? Then I can write cos HC is cos H A cos H B minus sin H A sin HB, and cos this theta will be basically pi minus some small epsilon, right? Okay. Yes. So then this will become, this cos h pi minus epsilon will become minus cos epsilon, which is close to 1, right? So this becomes minus 1 plus little o of 1, right? So this will become cos h A plus B plus little o of sin h A sin HB, right? Okay, and so if I multiply things by 2, so then 2 cos HC is this 2 times this, and so this is e to the c into 1 plus little o of 1 is e to the A plus B, and then I take this common, I'll get 1 plus this thing is when I divide this by e to the A plus B, I'll get a constant big O of 1, and then there's a little o of 1. So 1 plus little o of 1, right? And so therefore, I'll get that C minus A minus B is greater than or equal to some minus delta, right? Is this clear? Yes?
Yes.
Yes, sir.
Okay, so therefore, this mod xz minus mod yz is close to mod xzt minus mod yzt, right? And so then we're done, right? Because I get that mod xz minus mod yz. This is equal to mod xzt minus mod yzt plus little o of 1. And this is equal to, because zt is close to yt, this is mod xyt minus mod yyt plus little o of 1, right? Because mod ztyt is little o of 1. And now for t large, this is close to the Boseman function, right? B x y xi. Because this is along a geodesic ray from y to xi, right? So this is equal to Boseman function plus little o of 1. Is it clear? Okay.
Yes, yes.
Okay. All right. So so we have this, and now I want to say something about the relation between different visual metrics. How are they related? So if I have x and y, so if I look at the visual metric, based at x, so this is e to the minus Gromov inner product, right? And if I look at the visual metric based at y, it's e to the minus this Gromov inner product. So if I look at rho y xi eta whole squared divided by rho x xi eta whole squared, then this is e to the minus 2 Gromov inner product xi eta y plus 2 Gromov inner product xi eta x. And what happens when I take the difference of these Gromov inner products? So this minus 2 Gromov inner product xi eta y, that will give me a plus here and a minus here. And this plus 2 Gromov inner product xi eta x will give me a minus here and a plus here and a plus here, right? So what will this leave me with? This will leave me with a plus here and a minus here. This plus and this minus will cancel, and I'll have also a plus here and a minus here. So this is exactly this plus and this minus. This will be exactly the Boseman function x, y, xi, right? Yes, it's the distance from x to xi minus distance from y to xi, right? Interpreted as a limit, right? Similarly, distance from x to eta minus distance y to eta. So I'll get plus Boseman function of x, y, eta. Okay. Is this all right?
Yes.
Okay. So, so if I define a function, d rho y by d rho x of xi. So let me define this function of xi. this is e to the Boseman function x, y, xi. Okay. Xi belongs to boundary x. Then this I can write as d rho y by d rho x xi into d rho y by d rho x eta. Okay. So this is equal to rho y xi eta squared over rho x xi eta squared. Okay. So this is called, this equality is called the geometric mean value theorem. For these visual metrics, right? It's like a mean value theorem. You know, if I take square roots, then it's this distance with respect to the y metric divided by this distance with respect to the x metric is the product of, well, this function I want to call a derivative of the visual metric rho y with respect to the visual metric rho x. Why do I want to call it that? First of all, this function will actually be a continuous function of xi. So that's not hard to see, but I don't want to spend time. So this is actually, I'll just state this without proving. This is a continuous function of xi. Okay. So in this equality, what happens if I let's say eta tend to xi? So then star implies that the limit eta tending to xi of rho y xi eta squared over rho x xi eta squared. So this xi is fixed as eta tends to xi. If I assume, which is true, that this is a continuous function of xi, then this converges to d rho y by d rho x of xi. So this right hand side converges to d rho y by d rho x xi whole square, right? So I can remove the squares on all sides. And I get that the limit of the ratio of these two visual metrics exists and is equal to this function, this d rho y by d rho x of xi. So actually, what does this mean? This means that if I'm looking on the boundary, then, okay, so this is my space. So this is a point xi in the boundary. This means that this limit exists, means that if I approach xi from any direction, right, if eta is here or if eta is here, the limit is the same, right, as I approach from all directions. And what it means that is that, so if I call this, say, lambda of xi, then it means that if I take a small ball of radius epsilon for the rho x metric, so b, let me call this bx xi epsilon, right? Then this means points which are at rho x distance epsilon. So then the rho y distance will be approximately lambda epsilon, right? So this bx epsilon is close to by xi lambda epsilon, right? Is this clear? Yes. Okay. So in other words, if I look at very small balls or small spheres rather, right, then they have the same, in the limit, you can think of saying that these two metrics have the same infinitesimal spheres. So what I want to say is that the metrics rho x and rho y are conformal to each other, right? In other words, they have the same infinitesimal spheres. So let me quickly tell you what are conformal maps between Riemannian manifolds. So if f from Z1 G1 to Z2 G2 is a diffeomorphism between Riemannian manifolds, okay, then we say F is conformal if F preserves angles, right? So this is like in your complex analysis. Conformal maps are maps which preserve angles. So that means DF preserves angles. And this is if and only if for all x in Z1, there exists lambda of x positive such that norm of dfx v is equal to lambda x norm v, right? For all v in the tangent space at x, right? Is this clear? Yes?
Yes.
Right. Remember, what does it mean to preserve angles? Angles means you look at inner product divided by product of norms, right? And this quantity is preserved under DF, right? Yes?
Yes.
So this quantity is preserved. It's easy to see if and only if the inner product is preserved up to a scalar, right? Yeah. The inner product will be of df v dfw will be lambda squared times the inner product of vw, right?
Yes, sir.
Right. And so this is if and only if norm dfx v is equal to lambda x norm v. In other words, the ratio you see norm dfx v by norm v, this is constant independent of the direction v, right? This is constant equal to lambda x, you see? So what does this mean? This means that f df stretches the same in all directions, right? So therefore, if I take a sphere in the tangent space, say this is a sphere of radius r. This goes under dfx. So this is in tx z1. This will go to a sphere of radius lambda r, right? Yes. So
Do you mean r times lambda x?
yeah, lambda r, right? Lambda times r, right? There's lambda is lambda of x. I'm not writing the x. That's all. Is this okay?
Yes.
So spheres map to spheres, right? Spheres map to spheres. Okay. All right.
Yes. Yes.
Okay. Now, what is this limit? So lambda x is therefore equal to norm of dfx, right? Yes? Because it's the sup over all v of norm 1 of this quantity, overall v non-zero, and this quantity is constant. So it's the sup is equal to this constant, which is lambda x, right? Yes? Yes?
Yes, sir.
Okay. And so what is this? This is equal to norm dfx v over norm v. And this ratio I can write as a limit t tends to 0 d fx f gamma t divided by d x gamma t, where gamma 0 is x, gamma prime 0 is v, right? Yes? Okay.
Yes.
But now this is the same for all v, right? This is for all v. I have this. So this is actually the limit, as I can write this therefore as a limit y tends to x from any direction, distance fx fy over distance xy, right? Okay. Yes, is this clear?
Yes.
Okay. So what we find is that f is conformal if and only if for all x, the limit y tends to x of d fx fy over dxy exists and is positive and finite, right? Okay. Yes. Is this clear?
Yes.
Now, this last definition, this makes sense. This only depends on the metric D, on the distance function. So this makes sense for metric spaces, right? This makes sense for metric spaces without any smooth structure. Right? Yes?
Yes.
Okay. So we can define what is a conformal map between metric spaces, right? Okay. So can define. So this limit, we will call this, let's say mod f prime. Okay. All right. Because it's the norm of df, right? In the smooth situation, it's the norm of df. So this is a derivative of a sort, right? I can call this mod f prime. All right. So we can define conformal maps between metric spaces. All right. Is this clear? Yes.
Yes, sir.
Okay, if this limit exists and is positive and finite for all x in the domain, all right? And then we call this the derivative of the conformal map, all right? So we call this the derivative of the conformal map. So it's a positive real valued function, right? Okay. Okay, let's stop and start another meeting. This one is almost over. So.